to continue with the examples with the constant string triangle. I'll just finish the one that I started on Wednesday, and then I'll also do the other example. So for the one that we started on Wednesday, we had this mesh in the way that it would be given to Abacus, the coordinates of the nodes, and then the element connectivity. This is the mesh right here. And we are given these nodal coordinates for the displacements. So we are told that the first node has displacement 0, 0, second node has displacement 0, 0, then minus 0.1, 0.1, 0.1, 0.1. And we are asked to first plot the displacement along the line shown in the figure. So the line of y equals 0.5. So let's go to the Python notebook. This is what I started on Wednesday. Just importing the general packages. Then the main thing that you need is the shape functions and the derivatives. And that one you can get for the triangle from one of the previous lectures, either PL4, I think they are there. Yeah, they appear in multiple ones, but I think for sure they appear in PL4, so you don't have to code them yourself. So I'll just run that. And this I started already, that you have the node x coordinates, again, just exact same information that I was given in the mesh. So 0, 0, 0, 0, minus, sorry, 0, 0, 2, 0, 2, 1, 0, 1. So those are here, 0, 0, 2, 0, 2, 1, 0, 1. Then the element connectivity is, for element 1 is 1, 2, 4, for element 2 is 2, 3, 4. So for element 1 is 1, 2, 4, for element 2 is 2, 3, 4. I have to adjust this line right here, just to adjust and subtract 1 from the elements, just because for Python in the indexing starts at 0. So for element 1, I'll do it manually first, and then I'll do it reading out of the element connectivity array. For element 1, I want to plot the displacement interpolated over the line x is anything, right? So x is a bunch of points between 0 and where it ends for element 1. So to plot along this line, I need to move x from 0 to this point right here, because that's the last point of x still in element 1. And you can see that if this is length 2, then this is 1. And then y equals 0.5. So that's what I need to plot. I need to fix y at 0.5 and to move x between 0 and 1, let's say 100 points. Now, how do I interpolate any function? If you remember, the u vector is just the sum of the shape functions times the nodal values, u vec I. That's on the same slides as here, so if you go, you need to scroll up, but you can see here that the u vector is the sum of the shape functions times the x values, the shape functions times the y values. So here I'm first writing it. This is not correct. This would throw an error, but we need to get to something like this, right, where we are evaluating the functions. Now, where are we evaluating the shape functions? Well, we are evaluating for all of these x's, but only for y equals 0.5. I also gonna tell you that this is gonna throw an error because this is a vector and this is just a number. So we'll complain that when we are trying to evaluate the function, we are passing a vector, but also just a number. So it will want us to pass 2 vectors, for example. So I already know that this will want me to pass a vector of 0.5s. But it needs to be consistent, the dimensions of the arguments of the function, otherwise it will complain. All right, so this is the structure. Now, what is u1x, u2x, and u3x? Well, those are the x coordinate of the nodes of element 1. Here, I'm gonna do it manually first. So, get nodal displacements of node 1, of element 1, manually. By manually, I mean that I'm gonna go to the drawing and I'm gonna say, okay, element 1 is made of nodes 1, 2, 4. So this right here is the first node of the element. So this one, what are the x and y coordinates of this? So this is node 1 and has, displacement 0, 0. So u1x is 0 and u1y is 0. Okay, then the element is 1, 2, 4. The second node of the element is the 2 right here, and that one has displacement 0, 0. So okay, so that one has also 0, 0. And then finally, the last element, the last node of this element is node 4, this right here, and that one has displacement 0.1, 0.1. So u3, it's global node 4, but it's the third node of the element. 0.1, 0.1. Not u4, u3. And that's it. So hopefully this, well, this didn't like it. Oh, because I forgot that that's the other thing. So these shape functions taking not just x and y, but also take these values of the nodal coordinates. So I also need those. So I'll just put it here. Get nodal coordinates manually. So x1 is 0, y1 is 0, x2 is 2, y2 is 0, x3 is 0, y3 is 1. And then here I just need to pass x1. What is the order? x1, y1, x2, y2. y1, x2, y2, x3, y3. So like that. And same for the ones here. Okay, so now I did it. And now I have ux and uy. These are vectors because they have evaluated, you see there's a lot of values. Because I have evaluated at a bunch of different xy. Well, y was 0.5. There we go. They are all the same, so hopefully I did it correctly. Yeah, but let's just double check. So x1, y1 is 0, 0, 2, 0, and then 0, 1. I just need to check if it is 0, 1. Yes, 0, 1. So again, 0, 0, then 2, 0, and then 0, 1. Sounds good. So that one is, I can plot it. It's constant. You can see that it's constant. Yeah, and it's just because these all are 0. So really the only thing that is non-zero is the contribution of the third node. Yep. Now, that is manually. Let me redo it, and I can plot it. It's a constant, but I can plot it. plt.plot x comma, for example, ux, and then I'll do it in two separate plots. This is just a constant, and then I can plot x comma uy. So between 0 and 1, the value of uy is also just 0.5, and it's a constant. For element 2, I also need to do this for element 2. I would have to do a similar process, right? So I would have to, again, define what the x should be. Now it should be between 1 and 2. The y should be between, the y should still be 0.1, 0.5. So still this, but now this should be between 1 and 2. And then what I don't want to do is I don't want to do these things manually every time. I want to do this by reading the node X array, by reading the node U array. So I don't want to do that manually. So for this one, I'm gonna do it. I'm gonna read out of the elements array. So what should be x1 for this element? So if you go to PL4, you'll see that I always do this. I always define the nodal numbers. So this is out of the elements array. So elements, and now element 2 with Python indexing, this is 1. So this is node 1 of element 2. Elements 1, 1. This is node 2 of element 2. Again, the indexing is just from 0, so that's why it looks a little bit different. So 1, 2 is node 3 of element 2. And then these are the correct numbers. Then I just need to go to node X and read n1 x coordinate. And then for the y, I just need to read that y coordinate. For x2, I just need to read node 2. And for x3, I just need to read node 3. Much simpler. And because this will work for U and X. U1, U2. They also should have, I should have X, Y, X, Y, X, Y. And then instead of node X, it's node U. Elements is not defined. How did I define the... I did define as, maybe I didn't run this. Yeah, there we go. Anyways, so this now have the correct values, but the nice thing about this one is that in order for this to work for element 1, the only thing that I need to change is this. If I do this, then this is element 1. And then if I do this, this is element 2. That's it. That's the only thing I need. So Then the last part I can just copy. The last part is the same thing, so I just need to pass x and y and then just plot it. And then I feel like something is wrong. I need to check what I am doing that is wrong. Because I don't know if they should be constant and the same. Yeah, but this space is fine. As long as I'm passing the so xy, x1, y1, x2, y2, x3, y3. Yeah, I think this should be okay. I don't remember what the answer was, but this is definitely correct. And then u1x, u1y, u2x, u2y, u3x, u3y, that's correct. And then yep, this looks correct as well. And 1 and 2 and 3, u1x, u2x, u3x, and then all of them have xy, x1, y1, x2, y2, x3, y3. Yeah. Sounds good. So that's basically problem A. Plot the displacement. Now for the strain, I'll go back and plot the strain in a second, but what we should see is that the main thing, and this I'll reuse for the other problem in a separate video, but what we need is this B matrix. So the strain defined here is either you do all the sum that you need here, or you create this matrix and just multiply the matrix by the displacement. So you'll see that in a sec. So I'll just create the B matrix. Anyways, I'll need the B matrix later on. So let's do the B matrix very quickly for the strains, but I'll redo it here. So I'll just insert cell below. So I'll do it as a function. So calc B. And for B matrix, I just need x1, y1, x2, y2, x3, y3. And all I need to return is, well, I will need to calculate the area. And so that means that I need to call the area function. Where did I put it? Here. I need to calculate the area, and then I need to do NP_array. And so it's just y2 minus y3, y3 minus y1, and y1 minus 1, y2. So 2, 3, 3, 1, 1, 2. 2, 3, 3, 1, 1, 2. Hopefully that is correct. So 2, 3, 3, 1, 1, 2. Yes. 2, 3, 3, 1, 1, 2. Okay, that's the first line. Then second line is same but with x and flipped. So it's gonna be 3, 2, 1, 3, and 2, 1. So here 0, and then x3 minus x2 0, then x1 minus x3, then 0, then x2 minus x1. And then the last row is just this guy goes here and then this guy goes here, because these are the mixed derivatives. So x3 minus x2, then y2 minus y3, then x1 minus x3, then y3 minus y1, then x2 minus x1, then y1 minus y2. That's it, and that all times 1 over 2 times the area times that. All right, so 1 over 2 times the area times this gives me the B matrix, and then return BE. So this is what I'm gonna use for with the B matrix. So again, all I need is epsilon, let's say 1 for element 1 is going to be, there's one thing that I need to do because it's a matrix multiplication, right? So I need MP dot BE, and then I need what in the notes is called the DE vector, which all it has is just this UX UY but in a vector. So that one, I'm gonna call it the E, but I still need to fill it out. It's nothing more than the U1x, U1y, U2x, U2y, U3x, U3y. And I need to calculate BE from calc B. So I just need to call the function, calculate it, and then I just need to do the dot product, and that should be it. This I don't need to even print. This is constant. I don't need to plot. This is constant. So it's just 0.1.1. Note that the strain vector has 3 components. The first one is the strain with respect to x, the second one is the strain with respect to y, and the third one is the shear strain. All right, so that's for element 1. No need to calculate, no need to plot it. For element 2, again, no need to plot it. We'll just calculate it here. All we need is to call our calc B function, and then to put all the displacements in a vector, and do the dot product. Well, the matrix vector multiplication, not R but 2. Let me print what I'm printing. U1 is not defined, U1x. There we go. So that's the, I still think that something is wrong, because do they have the same strain? It doesn't look like it because of this minus 0.1. Oh, I guess, yes, I guess this one goes in a little bit and this one goes in a little bit. Also, they, even though it's minus 0.1 and the other one is positive, they are kind of doing the same thing. Okay, that makes more sense. yeah, so that's it. This is problem one. I'll stop right here and then I'll do a separate video for the other problem.